Hi, I'm Jesse. I'm from the University of Edinburgh, and I'm going to talk today about automatic differentiation via effects and handlers in OCaml. So here's an overview. First, I'm going to talk a little bit about automatic differentiation and effects and handlers. Then I'm going to introduce the main effect that I'm going to use to implement automatic differentiation and the two handlers used, specifically evaluation into normal floating point numbers and reverse mode for actually doing some automatic differentiation. Then I'm going to talk about some micro and macro benchmarks, and finally conclude. So automatic differentiation, what and why? So derivative-based optimization is important nowadays for machine learning, AI, scientific modeling, what have you. So a lot of that is achieved through automatic differentiation, which is a large family of algorithms to compute derivatives automatically based on a fixed implementation that you program. And the good thing about automatic differentiation is it's only a constant multiple slower than the original program. So if the original is 10 seconds, then the original plus calculating derivative will be like 30 seconds. There's also a wide variety of implementations and methods of implementation. But importantly, the available methods of implementation depend really heavily on the language's features. So the main idea of this work is that effects and handlers provide a practical basis for implementing automatic differentiation across the whole family. So let's talk about automatic differentiation and how we can do the chain rule in two different ways. So say we want to calculate this little expression over here, g of f of x at x equals a. So we can write that as a little straight line program. So x equals a, y equals f of x, and then g of y. And so let's look at the chain rule. So here's the chain rule from calculus. Hopefully you've seen it before. So we can calculate the derivative of g of f of x compositionally by using the derivative of g and the derivative of f. And we can make a more general version for not just two functions, but for three functions and n functions. And we can still do it compositionally, but now we have a multiplication of more than two things. And so now we can make a choice. We can either accumulate our derivatives from the right and do a right association of the multiplication, or from the left. And this is the difference between forward mode and reverse mode. So let's look at perhaps the more direct method first. So this is going to be forward mode. So we're going to calculate from right to left. And we're going to start the accumulation with 1. So what do? Well, we're going to add an additional variable to each of our original values. So x is going to get something with it, dx, and that's going to start at 1, which corresponds to the 1 on the left-hand side. Then we can calculate a derivative for y, so an intermediate derivative. So that's going to accumulate the derivative of f. So we multiply f prime of x times d of x. And next we can calculate g of y, and take our intermediate value d of y and multiply by g prime of y. So we've calculated the multiplication for the derivative from right to left. But we can also go from left to right. But left to right is a little bit weird, because in order to calculate g prime of f of x, we need to calculate f of x first. So we can get this nesting behavior and sort of a reversal of order of evaluation for some parts. So again, we're going to have an additional variable for each of our things. We're going to have bz, bx, and by. And so bz is going to be the left-hand thing, 1, and we're going to create other intermediate variables to accumulate the derivative. So in order to calculate the derivative of g, we need to calculate f of x. And then we're going to pair everything together. So we want to also return the final value, z, g of y. And now at this point here, because we already calculated f of x, we can calculate the derivative g prime of y. And then we can also calculate the derivative f prime of x and multiply by our previously accumulated value. So the important thing to see here is that we calculate f, we calculate g, and then we calculate g prime and then f prime. So we have a reversal of the data dependency order from the original data dependency in our program up at the top here. And that's why it's called reverse mode. But how can we improve this? Well, one thing we can do to make it more efficient in practice is to make it stateful. So how can we make it stateful? We do the following transformation. So as before, for each of our original variables, we associate something which is going to accumulate the derivative. And for by and bx, we're going to start them off at 0. And for bz, like before, we're going to start that off at 1. And we do the same math as before, except now we're going to overwrite the values. Now, I say overwrite, but what we're really doing is we're accumulating into them. And so in this case, it's the same as overwriting because we're only accessing them once. But in practice, if you have a function which has more than one argument, you're actually going to do some more accumulation, so it'll have more things done to it. So this is the more general version, which works for functions that have more than one argument as well. Okay, so this is all well and good, but how do we move beyond straight line programs? Because I only talked about a very simple straight line program. And the answer is effects and handlers. So effects and handlers, just a quick overview, what and why. Well, they're really good for structured user-defined side effects. They're like catchable exceptions, but allow continuing from the thrown location. And we've seen some stuff this week at ICFP talking about effects and handlers. They also provide really good abstraction, composition, and effect reuse via the algebraic effects and handlers of them. And it also allows for complicated control flow, which is the core thing we're going to use them for reverse mode. And as of OCaml 5.0, it's in mainline OCaml, so that's great. And what they allow us to do is to get a straight line view of the operations that we care about, in this case, the arithmetic operations. So what do I mean by that? So what we want to do is we sort of want to bubble up the arithmetic operations one at a time to get a straight line view of the program. So say we have a program here. We're going to have let x equals sine of 0.5 in some arbitrary program context C, and then we're going to use that variable x in some other program context D. And what we want to do is we want to bubble up this value, or this evaluation of sine of 0.5, and calculate that first. Now, this is a valid transformation if this sine here is just the normal sine function, so a pure mathematical function with no side effects. But in practice, like we saw, we're going to need to mutate some things and do some side effects. And what effects and handlers do is they let us do exactly this, even for effectful operations. So when we have an effectful version of sine, if we implement it as an algebraic effect, then we're also going to get this exact behavior, which is what we want. And not only do we get this bubbling up to get a straight line view of our program, we can also capture the rest of the program as a first-class continuation, and then just recover the original behavior by just evaluating this continuation k with the argument. And this bubbling up and capturing of the continuation is exactly what effects and handlers do. So we can use effects and handlers to get a straight line view of our program and then perform the normal reverse mode AD on it. So what's the main effect that we're going to use? So I've called it smooth. Smooth just means you can differentiate a function any number of times that you want. So that's why I've called it smooth. And we're going to first define some helper data types to represent the functions that we're going to allow to be differentiated. So I just have a small collection here, but you can extend this to have as many number of functions as you want. So we have nullary, unary, and binary functions. So a nullary function taking 0 arguments is just going to be the constants. So given a floating point number, just have a constant that represents it. For unary operations, we have negation, sine, cosine, and e to the x. For binary, we have plus, subtract, times, and divide. And we also have another helper data type arg, which is going to help us remember if we're differentiating a binary function with respect to the left or right argument. So with our helper functions, we can define a module type smooth. So this module type smooth is going to have a type inside of it, t, and that's going to be our numeric type. So for example, it could be floating point numbers. The next thing we're going to do is we're going to register our effects by extending the extensible variant effect.t. So we're going to have 3 effects for applying functions based on its arity. So nullary, unary, and binary functions. And so we see here, for example, a unary function takes 1 argument, and it's going to apply the unary function. So it's going to give 1 result back, similar for binary and for nullary. So we're also going to ask that we have some helper functions to actually call these effects. So C is for constant, this is for negation, so on and so forth. And then we also have some helper things which just perform these effects directly. And finally, we're also going to carry around the derivatives of the unary and binary functions. And note here, for the derivative of the binary function, we have to also specify if we're differentiating with respect to the left or right argument. So what are we going to do with this module signature? Well, the first thing that we're going to do is we're going to define a base module smooth. So this base module smooth, well, functor actually, is parameterized by a type t, which we can pass in. And basically, we're just going to implement everything that I said above. So here we extend the variant again. And now we say, for example, for negation, what is negation going to be implemented as? Well, it's actually just going to perform the effect of applying a unary function, specifically the unary function negate. And same for these other helper functions down here. So now we get to the interesting bit, the derivatives. So here we can record the derivative of all of our unary functions, so we can match on it. And if we look at the first example here, negation, the derivative of minus x is just minus 1. But note here that we're using the same effectful operations which we just defined. And what this is going to allow us to do is it's going to allow us to nest and inject effects into our implementation, which is going to allow us to later nest our reverse mode to create new automatic differentiation algorithms based on old ones. So that's the derivative of the unary functions, and we also have derivatives of the binary functions. So for example, for multiplication down here, the derivative of x times y with respect to x is just y. The derivative of x times y with respect to y is just x, so on and so forth. Okay, so we have our base module. Let's actually use the effects. So the first thing we're going to do is evaluate our operations just in terms of floating point numbers. So we're going to define a module evaluate, and the first thing we're going to do is just include the base module, so this just saves us some time for now. And we're going to instantiate the type of that numeric type to just floating point numbers. And now we're going to define a handler. So here's the current handler syntax in OCaml 5. So we're going to define an effect handler evaluate, which takes a computation returning something of type A and produces something of type A after handling all the effects. This clause here, return C, says what are we going to post-process our final result with? Well, we're not going to do anything. We're just going to leave it alone. What are we going to do if we encounter any exceptions as we execute? We're just going to re-raise them. And now we reach the actual effect handler part. So this effect handler here, we're going to match on all the effects that we see, but we're not going to handle all of them. We're only going to handle the 3 which we defined ourselves. So let's look what happens for handling the constant case. So for the constant case, we say, OK, if we see the effect app0 for some function n, what are we going to do? Well, we're going to be given the continuation, which we can use to resume our program. And if we see constant, which is the only option that we have now, what we're going to do is we're going to use the continua function along with the continuation k and pass that value x just back into the program. So for this case, it's very simple. And for the other cases, it's also relatively simple. U is going to be a unary function, and x is going to be a float because we instantiated the type of the type in our module smooth to be a float. And so now we can just continue the program, and every time we see an operation, we just replace it with its actual definition in terms of floating point values. Okay, so this handler isn't very interesting, but this is our base case. So if we want to take an effectful arithmetic program, we can just instantiate everything to floats and just interpret it that way. And here's how we use it. How do we use it? Well, we open our module evaluate, define some helper function that we want to differentiate, just squaring something, and then we use match with to actually handle an effectful computation. Specifically, the effectful computation is this function here. And what we're going to do is we're going to take a Boolean twice, and that's either going to apply square to itself twice or once, and then we're just going to pass in the value x, which we're going to either do square square x or square x. So here, we pass in the value true, so we're actually going to perform x to the fourth and x to the fourth at 5, and we're going to evaluate all of our effectful operations with the effect handler evaluate, which we just defined. And so indeed, this produces the correct result. So let's make a more interesting handler for reverse mode. So recall, this is the final program that we got. And I'll emphasize again the reverse dependency order. So here we have f and then g prime, and then f. And in order to create this reverse dependency order, we're going to do some interesting control flow by executing some stuff after we call continue. So for the reverse mode handler, the first thing that we're going to do is we're actually going to define a new data type of pairing a value along with its mutable companion. So here we have m paired applied to some type t. So this type t can be some other thing which supports automatic differentiation, or it can just be, for example, floating point numbers. Then we're going to define a functor, reverse. Now note, this functor is going to take a module of smooth type. So reverse, the definition of the effectful operations which we're going to use in reverse are parameterized by some other module smooth. So if this module here, t, is the evaluate module we just defined, then all the operations that we're going to see in the body here will be on floats. But we'll also see that we can instantiate this module with anything else as well, and that'll allow us to nest our AD modes. So we're going to include our base module again, but this time our base type is going to be m paired of the input type. And now we can start defining our handler again. And we don't do any post-processing. We re-raise the exceptions. And now we're going to match on our effects. So again, we have 3 choices. The constant case isn't very interesting, so let's look at the unary case. So the unary case, what are we going to do? Well, we have our function u applied to x. So the first thing that we're going to do is we're actually going to apply u to the value part of x. So that's the thing that we get in the normal forward pass of our program. And we're also going to initialize bv to 0 like we did before. And note here that app1 and this c here are effectful operations. So these will also require some enclosing handler to actually give them meaning later. Then we're going to continue the rest of the program. When we continue the rest of the program, this value bv is going to be changed. It's going to be accumulated into, and by the time we finish this line continue here, it's going to be non-zero if there's a dependency on the values in the final result. So once we do that, then we can perform the accumulation line, which we saw in the short example program. So we can take the derivative of u at x, multiply it by the b part of the value r that we defined up here, and accumulate it into the derivative of the input of our function. And we can do the same thing, or an equivalent thing, for binary functions as well. So this is taking advantage of the complicated control flow that we can do with effects and handlers by sort of reversing the data dependency order of the original program. So let's see how we can actually use this handler. So the right way to use it is in this helper function grad. So this helper function is going to actually calculate the derivative. So we take a function f, which we're going to differentiate at some value x. And what are we going to do? Well, we're going to do the same thing we've been doing, just initialize something to 0. And then we're going to use the actual handler reverse. So what we're going to put in reverse is going to be f evaluated at x. So this is going to perform a whole bunch of effects, which is going to be handled by our handler reverse. And then we're going to start the accumulation of the derivatives by initializing this value to 1. And this corresponds to the one that we had in our example program. And then when this match statement finishes, we'll have accumulated all of our derivatives. And so the only thing that remains is to just return the derivative, the final result. So here's an example using the derivative. We have our module e, and we pass our module e into the functor reverse. So this is going to take all of the arithmetic operations we saw in the body of the reverse mode handler and make them in terms of floating point numbers. So now we define our square function again, and now we can actually differentiate our function. So here we have the same function as before, and we're wrapping it in the gradient helper function. And this indeed will calculate the correct derivative. So we have square x, x to the fourth, and this will calculate derivative of x to the fourth, which is 4 times x to the third, and it computes the correct derivative. But not only can we pass evaluate into reverse, we can pass reverse into reverse to calculate second derivatives. So here, we use a gradient here and a gradient here, and we calculate the second derivative. And I haven't shown other implementations of other AD modes, but there's a whole family. And with this method of implementing via modules, you can mix and match all the modes that you want, and everything works hunky-dory. So I'm not the first person to do this. Casey is there. Casey implemented reverse mode AD with handlers, and Casey said, I think, that he was inspired by demystifying differentiable programming with shift reset, and they used delimited continuations. But we are the first to design a larger system, and also, which I'll show soon, do tensored valued operations, as well as do micro and macro benchmarks of everything. So let's look at some benchmarks, but first, what should we expect? So there's a great book on automatic differentiation by Grieve and Volter, and they show that for a composite measure of work, reverse mode is only a constant multiple slower than the original program. And indeed, their definition of work is quite nice. It involves memory fetches and stores, additions, subtractions, multiplications, and nonlinear operations like sine, cosine, exponentiation. And with reasonable assumptions, they prove that reverse mode should be somewhere between 3 and 4 times slower, depending on exactly what operations you're doing. So we ideally want to be only 4 times slower than the original program. So here's the micro benchmark. We're just going to calculate 1 over x. 1 over x has an infinite sum that you can use to calculate 1 over x. And we're just choosing this because we can calculate a prefix of the sum, and that can be our notion of work that we do. So we can just create a little recurrence here. So the first term is 1, and then we just multiply the previous term by minus x minus 1. So we can make just a little program to approximate the reciprocal, where we pass in the number of iterations, and this number of iterations is just how many terms of the sum we're actually doing, and that gets put into a for loop. So what we should expect is as we increase the number of iterations that we do, we should perform a constant multiple of work each iteration, so this should be on with respect to iters. So let's look at a graph and see if that happens. So indeed it does. So here we have evaluation mode. So if we just evaluate it in terms of floating point numbers, it is on with respect to the input. Okay, good. And reverse mode we see is also on. So if we put these graphs together, so note here these are log scales. So the fact that reverse is shifted upwards means exactly that it's a constant multiple slower than the original program. And if you calculate it, it's approximately an 8 times slowdown. So we didn't reach the theoretical minimum of 4, but overall, it's not that bad. So we validated the asymptotics of the automatic differentiation algorithms with some micro benchmarks. Let's look at some macro benchmarks. So the best automatic differentiation benchmark suite that I could find is by Schreier et al. It's reproducible by using Docker containers. It's extensible. There's a nice test harness. And it's also realistic. So they choose 4 different tests based on real machine learning and computer vision functions. Now, the problem of what I've shown so far is that if you have one effect call for each addition and multiplication and subtraction you do, it's not going to be efficient. So the solution is to move from scalar operations to tensor/matrix/n-dimensional array operations. So I use the OWL scientific computing library of Wang et al. I extended the smooth effect and smooth module to support 35 operations involving tensors and scalars and stuff. And I extended reverse mode to handle these new operation types. So specifically, we implement one of the objective functions in the benchmark suite for Gaussian mixture models. And the input to the benchmarks has 3 parameters, n, k, and d, where n is either 1,000 or 10,000. And k and d is actually the total number of input variables which we're differentiating against. So the x-axis in our graphs is just k times d. So here's all the tools in the system. There's a lot of different languages and a lot of different approaches. So there's manual approaches, which is just calculate the derivative on paper and write a program which calculates the derivative. So theoretically, these should be the fastest, one would hope. There's also finite differences, which is just f of x minus f of x plus a little bit divided by that little bit. And that's a really bad way of doing derivatives. So this is here to show you that hopefully all the AD systems do better than that. And then there's a whole bunch of other stuff, including industry standards like TensorFlow and PyTorch. So what do I mean by static and dynamic? In automatic differentiation, you can sort of do 2 big classes. Static basically means that you evaluate away all the control flow to create a static computation graph, a DAG, and then perform differentiation based on that. And you'd expect those to be relatively fast because you don't need to deal with any dynamic control flow. And dynamic means you're still retaining dynamic control flow, and as you go, you create some structure and then do something based on that. And so you'd expect usually, although in the graphs we'll see it's not always the case, that dynamic is going to be slower than static. And the work that we've done here is definitely dynamic. So ignore those red triangles for now at the top. Here's the OCaml stuff with handlers. And n is 1k at the moment, and the variables k times d are at the bottom. And also note this is a log-log graph as well. So let's compare it to the manual implementations. So we see here, okay, all the manual implementations in C++ are quite fast. And the finite differences is the one that's really bad up top. And that just shows that if you want to calculate a derivative, don't use finite differences. It's really bad. Okay, so let's look at the static implementations. So we can see here that pretty much all of the static implementations are doing better than us as well, except for some reason the Julia Zygote library is having a bit of a tough time, but I'm positive for Julia that the newer libraries are going to do better. But the benchmark suite is a little bit old, so Enzyme and some of the other newer stuff isn't in the benchmark suite. So let's go to the ones which we really should compare ourselves against, the dynamic ones. So for the dynamic ones, we're doing a lot better. So we can see here we're pretty much the same as eager TensorFlow, which is dynamic, and also the diff-sharp library in F-sharp. And here's another Julia stuff going on over here. And then we have PyTorch. So PyTorch, turns out, is really, really, really good. I talked to one of the authors, Adam Paschke, this week. And I'm like, oh, why is PyTorch so fast? Because in fact, PyTorch is even beating the manual implementations we can see when it gets higher. And his answer was, we spent a really, 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 really long time and a lot of effort making it really fast. And yes. So PyTorch wins, and indeed, when we look at the other set where n is 10k, PyTorch still wins. And here we see TensorFlow starts to beat us a bit, but then it either runs out of time and memory, so I don't know exactly what's happening there, but yeah. So conclusion, There's actually a lot more to say on AD and effects handlers. You can look at my thesis. So there's many different modes. So there's checkpointed reverse mode, which does a time and space trade-off. There's also higher-order functions and higher-order derivatives. There's also different languages, some with effect type systems, which can help you avoid some AD-specific bugs. So in my thesis, I also look at Coca, Frank, and F. And there's also mathematical correctness to consider. So using denotational semantics, I prove forward mode and a simpler, non-stateful reverse mode correct. So AD and reverse mode AD in this talk specifically requires complex control flow. Effect handlers enable a simple implementation which follows the math. And with a little effort and moving to tensor-valued operations, we are competitive among similar tools. So future work, I didn't realize this, but PyTorch, its C++ backend, which is the fast bit, actually has bindings in OCaml. So I tried this week to switch my bindings from OWL to the Torch bindings, but I didn't have enough time. So that might actually get us a lot closer to the PyTorch stuff, so we'll see. Also, I want to prove correctness of the stateful reverse mode, which requires doing some more work behind the scenes, and also custom functions. So if you implement a function, you can have AD calculate the derivative for you. But for mathematical reasons, you might know a method of calculating the derivative which is a lot faster. So putting custom function derivatives can be quite useful, and that might actually involve higher order effects. And you can read more about some of the stuff I talked about in the preprint. Thanks.
Yeah, I have at least one question. So your effect handlers do not have the continuation call in the tail position.
Nope.
Does that mean that the stack usage is proportional to the sequential length of dependencies in the program?
Yes. So actually, Stephen Dolan helped me out. So if we look at the example usage somewhere, you need to increase the garbage collector minor heap because indeed the amount of continuations you use directly increases the stack size. And so if you're not careful, you repeatedly go over the minor heap and create quadratic behavior. But I've been told that this is a sort of long-standing. Oh, I removed the slide actually. A long-standing thing in OCaml where that was sort of always the case, and now with the addition of effect handlers, sort of needs to be changed a bit so that this quadratic behavior doesn't happen. But in general, reverse mode AD is supposed to be linear in terms of memory usage, and so it's still correct with respect to the asymptotics, and with a change to the GC, you can still get the correct behavior. Yeah.
Maybe Stephen sitting on? Just a question. So what happens if your function you want to differentiate is parallel, uses multicore, for instance? Then
this doesn't handle it at all. And I think so for automatic differentiation, there's definitely a lot of opportunity for parallelism, both in the basic operations, if they work on arrays, and also in general, because ideally you're differentiating pure mathematical functions, but this work doesn't talk about anything related to that.
So yeah, you say you got the asymptotics right. Have you done more detailed performance analysis to see where these overheads are really coming from? Like, is it from the GC? Is it from the effects
no.
implementation?
But that's some good future work to look at. Yeah, thanks.
Thank you.